Today I'm going to talk about the effect of stellar activity on high precision transit light curve. My talk consists of two parts. The first, I will talk about the impact of activity on the transit light curve analysis and how much it affects our parameter estimation for the planet. And on the second, I will talk about the stellar activity, how it can affect the transmission spectroscopy and the planetary atmosphere study. So the stellar activity, mostly the stellar spot, can affect the transit in two ways. The first one, when the stellar spots are not occulted by the transiting planet. In that way, the total flux of the star is reduced, and as a consequence, we are overestimating the planet radius. For example, in the case of CoRoT2, it was 3 to 4% bigger than it should be because of this effect. But the other scenario is that when the planet overlaps with the stellar spot. In that case, you can see inside anomaly in the transit due to the overlap of the planet and the spot. In the case that those anomalies are very well identified, people decided to remove them from the light curve, and then they study the rest of the light curve, which might not be the best approach because you are losing a part of your data, which may introduce a bias in your estimation. So the better approach is to try to model those anomalies and clean them from the transit. So in order to do that, we develop a code that can simulate a transiting planet over the rotating spotted star, and it can generate the out-of-transit variation of the light curve and also the inside anomalies. For example, here for the case of HATB11, that it could perfectly produce both cases. So we can model them and then remove them from the light curve. But in most cases, when there are those anomalies not very clearly identified or they are in the error bar of your transit, you cannot identify them. So mostly people, they don't consider them. So we want to see how much those ignorance will affect our parameter of the planet that we estimate. So in order to do that, we generate a large number of mock observations using our code by considering those anomalies inside, and then we try to fit a transit model to them to see how much those anomalies affect our estimation. And we let the transit depth and the transit duration and also the mid-transit time be as our free parameter to fit. The first interesting result that we found that those anomalies can induce TTV signals, which for some cases can be in order of 200 seconds. This 200 seconds is in level of amplitude of several TTV candidates of the Kepler. So we want to call attention up to those people that are working on TTV that if you find TTV of 200 seconds, be careful, go and look to your star if it is active or not, or inside transit, can you see those anomalies or not? Then trust your TTV that is due to the gravitational perturbation. And recently, and more accurately yesterday, it was a paper by Maze that he showed that using those TTV induced by the stellar activity and combining those information with the out-of-transit slope, you can get information about the orbit of the planet, about the prograde and retrograde orbit of the planet. So those TTV induced by the activity are not just problems, they can give us also information about the orbit of the planet. The second result, we found that those anomalies can underestimate our planet radius estimation by 4%, and also they can cause the transit duration to be 4% longer or shorter than its actual value, which can affect the inclination of the planet that we estimate. So now I will move to the transmission spectroscopy. The transmission spectroscopy is one of the most useful method to study the planetary atmosphere, and it's based on the observing the transit of the planet in different wavelengths. And you determine the planet radius as a function of wavelength, and then you try to interpret it by assuming the planetary atmosphere, and you can constrain the molecular composition or the thermal structure of the atmosphere by interpreting those variation in the planet radius. But since this method is also based on the transit, it should be affected by stellar activity. In most cases, people were just considering those non-occulted stellar spots in their study. Only in one cases which they clearly saw the anomaly inside the transit observed by HST, they tried to remove that data point from their data and said that, okay, this measurement, we should not trust it because we see it clearly, the transit anomaly. But we want to see again that those people that they don't really care about activity inside their transmission spectroscopy, how much their measurement can be affected. So we again try to quantify this impact, and we modified our code to be able to produce it in different wavelength, the transit. And we again generate a large number of transit with those anomalies. And in this case also, we consider the overlap of the planet with the bright spot plage on the stellar surface. So interestingly, we find that those overlap and one anomaly in the transit, especially on the short wavelength, can cause underestimation or overestimation on the planet radius up to 10%, which was significant. And for example, for a plage with 100 Kelvin difference with the surface of its star, and for a Jupiter-sized planet, with the maximum filling factor of the plage, it can cause 10% overestimation for the planet radius. Then we went to study two famous cases that they had the transmission spectroscopy. One of them was HD1 89733b, which is a hot Jupiter rotating a K dwarf, and it is one of the well-studied planets for atmospheric study. And they observe a strong increasement in the planet radius toward the short wavelength. But this planet is orbiting a very active star. This star shows 2% variability in photometric every 12 days, which is the rotational period of the star. So it's reasonable to assume that the planet during its transit is overlapping with the plage. So we assume that, and we find that we can easily reproduce that increasement in the planet radius toward the short wavelength, which was interpreted as a Rayleigh scattering in the planet radius, by just assuming overlap with the plage. So we want to call again attention to the people working on transmission spectroscopy. The amplitude of the Rayleigh scattering that you expect, it can be easily reproduced by a stellar activity, occultation. And the second case was GJ3470b, which was also observed in transmission spectroscopy, and also they observed increasement in the planet radius, and they also interpret it as a Rayleigh scattering in the planet atmosphere. But again, that star is active, and it shows 1% photometric variability. And by assuming same overlap with planet and the plage on the surface of the star, we could reproduce same increasement in the planet radius in the shorter wavelength. So as a suggestion to people that they were working, we suggest two strategies to overcome this issue. The first one was to observe in the given wavelength for several times, so you can see if your planet radius vary as a time. Then you should not trust your planet radius because it's affecting by the stellar activity. Or if it is not possible to do several transit, you can do out of transit observation in multi-band photometry. So from that, you can have estimation that do you expect inside the transit to have stellar spot or plages that can affect your estimation or not. So I stop here with my conclusion. Thanks.
Of questions in the audience. I have a question myself as well, but I won't go first because that wouldn't be polite. So, Eike, maybe?
Thank you. How about observing the transit in spectroscopy in the calcium lines directly? Then you should see very largely this effect, right? In the calcium lines, they trace the plage.
Yeah, yes, because the contrast is higher, yes, you can see it better. Yeah.
But has this been checked? Or
I didn't check it yet.
Okay. There was a question from Katja here.
Yes, yeah, this is some very interesting work. For the simulations that you showed, you assumed plage occultations, but you could also do spot occultations for this active star and get a different effect, right?
Yes, you can get the negative.
Why has nobody observed the opposite effect in real data with spot occultations?
I didn't check the other system that maybe there are other systems that they observe this, because here I show that the negative one can happen. I didn't check for the negative one. We were interested in those blue sky planets.
Okay, I'm going to use my prerogative as chairman and ask a question myself, or rather a comment, which is that this interpretation of the Rayleigh scattering slope as potentially due to plage or spots is a very interesting one, and one that we should certainly bear in mind, but it requires an extremely contrived spot distribution, which are basically right under the transit and nowhere else. And that's not actually compatible with the rest of the information in the case of HD 189, where we know from the frequency of large spots being transited that the transit chord is about as spotty as the average of the rest of the star. I don't know if you want to respond to that.
But no, it was just suggestion for future. If you have an active star, you should take care of this.
I completely agree with that. I see a question from Luciane right at the back. Anyone else?
Hi there. Thanks for this really spooky story. It should scare all the exoplanet people. I have a question. Can you clarify the geometry that you're using for the plage? Because in your cartoons, it appears that you're using essentially a bright spot, which is not quite correct for plage, right? Because plage is most visible at the limb of the star as opposed to in the center where it would most affect the transit. And so I'm wondering if you have any plans to include different geometries for where you would expect those bright regions to most affect the transit shape.
We consider the overlap happened when the plage are in the center of the star, and we consider that the plage has a different limb brightening effect. So we consider that when they are in the middle, they are not the highest contrast that they have. But when they are on the limb, they cannot change the planet radius that much. So they are brighter, but they cannot change the depth of the transit.
Okay, we have time for one last question. I saw Vivian.
Yeah. Hi. No, it's a very interesting question to wonder on the effect of this plage. I think that, so what you're doing is that assuming that you're crossing a plage at the middle of the transit and then using only this transit-like curve at different colors, you find the signature of the ray scattering. So I think that for planet like HD 189, for example, but first, such a plage at the middle of the transit, I guess if we see spot in the transit, we should see in the data the presence of a plage similar to this and be able to remove this effect unless the planet transits completely plagey area of the star.
But usually plages are very big also. We should take into account that they are much bigger than the spot. So when you have the overlap, maybe you cannot see it as you can see it good for the spots. Okay. So the filling factor of them can reach to 6% of this.
But you're using filling factor around 1.5 or 2, no, right?
Yeah,
this
one,
data here.
Yeah, we didn't need bigger one, but it can
you
reach.
could have big.
Yeah.
And the second point I was wanting to point is that all those observations are done actually at different time for HD 189. Yes. Yeah. And so you'd expect from that a more scatter on the points, whether by chance you had a plage at this moment or no plage at this moment. And at the end, different observations like this that happen at different time should not align with the ray scattering. And the very last point that you didn't mention is that in the That's what we saw actually in the Desert 2011 paper, where we had this point in HD2, I think in HD 209 for the presence of water, and so we explained that the variability between two observations that were taken at two different times could actually be explained by a spot feature that was outside the transit that you could retrieve with the variation of the light curve outside transit. So yeah, I was pointing out that I would more expect of a scatter of the points. Thank you.
No, I agree that it was a simple assumption, but for a very active star, I think we can assume this assumption, that it can overlap with the plate every time. But yeah, it's a simple assumption.
So thanks again. Let's thank Mahmoudreza.